This segment we're going to talk about the second law limits on cycle performance, and this will be the first part in a series of segments. So you might be wondering what the highest possible thermal efficiency for a cycle, what's the highest possible one you could get? We know it goes from 0 to 100%. So is 100% the best that you can hope for? Well, we'll see. What's the highest possible coefficient of performance that you could have for a refrigeration or a heat pump? That's not expressed as a percent, but what's the best one you could hope for? Is it 4? Is it 50? Is it 100? These are the questions that we're going to answer. So to answer these questions, we need to define deviation from ideal thermodynamic behavior, and those deviations are called irreversibilities. An irreversibility, or a process, is irreversible if the system and the surroundings can't return back to their initial state, both return to their initial state exactly as they were in the beginning. So deviations from, or common sources of irreversibility in engineering that you'll encounter are friction. So let's look at a reversible expansion or compression process. In other words, we don't have any friction. So here I've got a piston cylinder, and it looks like the system and the surroundings are both at thermal equilibrium. And let's say I've got a compression process. The temperature of my system goes up because I've compressed things. Pressure goes up, temperature goes up, and maybe the system goes up as well, so that both of those things are in thermal equilibrium if heat transfer is allowed to occur between those two things. And now let's say I expand it again. And so I expand it, everything goes back, it's 25 degrees Celsius, and my surroundings, if it comes into a thermal equilibrium and heat is allowed to be exchanged between the system and the surroundings, it comes back up to 25 degrees Celsius. So you could see that the initial state and the final state are exactly the same. So that would be the case if you had no friction. But now let's look at the case that you do have friction. So same scenario, your system and your surroundings are at 25 degrees Celsius, and now I compress things, and like before, it came to the system was, you increase the pressure, temperature went up to maybe 30 degrees Celsius, and if I allowed things to come into thermal equilibrium, maybe at 30 degrees. Well, if I look at the interaction between the piston head and the cylinder wall itself, what I'll see is there is friction, and there's going to be frictional heat that's generated as that piston head moves up and down. And so it's going to add heat to both the surroundings and the system itself. And so instead of maybe going to 30 degrees, now it goes to 31 degrees. All right, now it expands again, and before it went back to 25 degrees Celsius. Both the system and the surroundings are allowed to come into thermal equilibrium with one another, but because there's frictional heat generated as it slides back up again, now I go, instead to 25 degrees, maybe I go to 26 degrees Celsius. So you can see that the initial state and the final state are not the same. Now let's see, maybe I've got heat transfer through a finite temperature difference. That's another source of irreversibilities encountered in engineering. So what we mean is when we say finite temperature difference, we mean not really, really, really close to zero. So maybe you've got a body at 30 degrees Celsius, you got a body at 10 degrees Celsius, and of course your heat is going to be transferred from the hot to the cold. Well, the only way to reverse that, you can't reverse that without having any consequence on the surroundings, because the only way to reverse that would be to throw a refrigeration cycle in between there. Another source of irreversibility, unrestrained expansion of a gas or a liquid to a lower pressure. So popping a balloon and allowing the gas or the liquid to escape. You can see how you're not going to be able to reverse the process without something happening in the surroundings. The surroundings doing something to make it go back the way it was. And there are lots of other sources of irreversibilities as well. Those first three are the most common. The first two are the ones that I'll reference the most in this class. So, all right. Well, thank you for watching, and I hope that was helpful.